There's not many people left, so that's good. Hopefully we're going to scare them and excite them. Exactly. Goodbye silicon chips. Hello DNA strands. Doug, is that going to happen? Are we going to say goodbye to silicon soon? Tell me about this technology.
Well, I don't think silicon's going to go away anytime soon, but we're going to see DNA showing up in the data centers really soon. We think we've got a plan that will allow us to use DNA for storage that will eventually replace tape and disk drives in the data center.
Emily, where, in terms of speed towards this technology, how far away before we get there?
So right now we've already demonstrated that DNA is the best media to store data for the very long term, and we've done many projects with Microsoft, and every time where data is encoded, 100% of the bytes are recovered. And so already today, it works. The benefit is the permanence. It's permanent for thousands of years. The density. The only thing that we don't have yet today is the price. The price point is still very high. But that's just a question of time as we move to better and better DNA synthesis technology. That price goes down, and at some point it becomes viable to deploy widely in the marketplace.
Doug, give me a little bit of a history lesson here, because this is new technology to me, but it obviously isn't new to you. Can you kind of wind us back a little bit and start talking about where this idea came from and how it started and how it developed?
Yeah, I joined Microsoft 4 years ago to work on the future of computing. And we think we've been working on quantum computing, and we think we've got a solution that says the world's computing requirements will be met within 4 to 6 years. The next question was, how do you store all of the data? And I had the lucky coincidence of meeting 2 colleagues that had just come back from Cambridge, where they saw Nick Goldman talk about the very first data that was stored in DNA. Emily was a co-author on that paper, and we started talking about it. Initially, it seemed like a crazy idea, and a lot of the things that come to pass actually start off as crazy ideas. We were working on it 3 years ago. We pitched it as an internal project startup for Microsoft, and Microsoft loved the idea, and we've been working on it for 3 years.
Were there other technologies that were competing with it that it got eliminated?
Yeah, absolutely. At the time that we started looking at DNA, we looked at everything under the sun, everything from disaggregating silicon bits, finding ways to take storage devices and lifting them off of silicon, to using lasers to write very nano writing things into silicon, and using atomic force microscopes to actually read them back. So we looked at very, very exotic techniques, but DNA has this, beyond what Emily talked about, it has this relevancy where we think that people will always want to read DNA as long as they're humans, whereas we're losing track of our ability to recover storage on who could recover a floppy drive today, or these tape drives that people are using for storage. And so storing DNA is a natural way to do it. It's incredibly dense, always relevant, and it has very, very high reliability. So that it's a key technology. It beat everything else we looked at.
Emily, can you kind of explain to me, I'm a consumer, when I walk into the store and want to buy myself a hard drive, I kind of buy a physical object, a bit bigger than this. I spend €100 or something. What do you imagine this technology kind of looking like? What am I going to buy when the price is affordable for me?
So there are many options. Yes, you can go in the store and buy a hard drive, but the data on your phone is stored in the cloud by Apple or Samsung. So you also have a lot of data in the cloud. And so if you look at in the future, where most of the data will be stored at your home, or will be stored in the cloud. And so most likely it will be in the cloud, so you can imagine big facilities. such as an Azure facilities of Microsoft or others, but where if you need data to be stored at a very, very high confidence that it will be there for a very long time, then you upload that data, it gets written in DNA, gets stored. If you want, you could get that DNA sent to you if you want to be the one putting it in your safe. And then when you need the data back, you either send that small piece of DNA back, or you ask the cloud to bring the file back on your computer.
I'm a bit of a beginner on this. So you're gonna make a little bit of DNA and then encode stuff onto it, or you kind of encode it as it goes, or how does it work?
Yeah, so the way it works is there is some latency, which means that we have a little bit of time to write it. But once we get the file, it gets, so when we do a project with Microsoft right now, usually Microsoft does the encoding. So they do the conversion from zeros and ones to ACGT, and they have some magic formula that I don't know, but Doug can talk about it. Then the file gets sent to Twist, that ACGT file, and then it goes on our machine. And our machine is a 3D printer where we print DNA with a 3D printer. And, as you may know, DNA is 4 letters, ACGT. So we have a printer with 4 inks. There's a bottle of A, a bottle of C, a bottle of G, a bottle of T. And so the DNA gets made. It takes a few hours. And then the DNA is collected. And that sample that is now stable for a very long time.
What does that look like? Is it kind of microscopically small?
Yeah, so if you imagine 1,000 hard drive, that's about 1 petabyte. And if we make 1 petabyte of data in DNA, it's the size of a grain of salt. Right? So it's extremely small. The density is massive. And so you have to be careful that you don't lose.
I mean, I often say about micro SDs, they're a bit on the small side. I mean, if I could accidentally swallow my data, that wouldn't be great. Surely that's an issue, isn't it?
Well, I mean, you eat DNA all the time. Like,
yeah.
But
it doesn't have important information on it normally, though, right?
Well, if you eat it, it's gone.
Yeah.
Exactly.
Doug, how do you imagine Microsoft rolling this out, commercializing it?
Well, Microsoft is very interested in turning it into data as a service. So we would like to be able to store all of your data. As Emily said, the density is incredible. We've estimated that we could take all of the accessible information on the internet and store it in something smaller than a shoebox. And so imagine that for Microsoft's data storage service is that we can take your data, store it in our cloud for safekeeping for you, and then retrieve it when you want it back. We think about services where the price to store it might actually be free, and then we only charge you when you want your data back.
Okay, it's free to give it to you, but then I have to buy it back.
Well, it's still your data.
Right.
Well, we're happy to give it to you.
You're looking after it nicely for me.
Yeah, that's
very
right.
kind.
Yep.
And then how much will I have to pay you to get it back?
It would be, well, in order for it to be competitive, it would need to be price competitive, so it wouldn't be something that would be a crazy price.
How does this technology really compare to what we've got at the moment? How much of a leap forward is it?
It is 6 orders of magnitude, so it's 10,000 times more dense than the densest storage media that we have today. So 10,000 times more dense is quite a bit. And again, Emily talked about taking hard drives, and it's the size of a grain of sand. We've looked at data centers that are full of hard drives, and the data center shrinks to something that's smaller than a shoebox. And so it's a huge win.
Where would you keep your shoebox?
Well, the interesting thing about DNA is it's incredibly stable. As you know, that there's been DNA recovered from fossilized creatures. So the thing that we want to do is preserve it so that it stays for a very long time. It's stable, and so we're looking at encapsulating it into glass beads, and then in basically keeping it in what looks like a fairly conventional refrigerator. DNA is our DNA is most stable when it's not above 98 degrees C, so we would 98 F. So we'd like to keep it close to right around 5 degrees centigrade.
I'm wondering how would I then copy this information, because there's nothing I like better than to give somebody a USB key with something on it and pass it on to them. Can I do that?
Yeah, I mean that's the beauty of DNA. There is a biological process called PCR, and you can copy any DNA in 1 hour for $1. So you could take an entire data center, and for $1 you could copy it and make millions of copies. So and it's extremely accurate. So the copying is actually very, very easy. And you can even do something that's pretty cool, which is in the encoding, if you're careful about adding a right barcode for each file, you may be able to copy out just the file that you want. So you have the shoebox and you want something, you'll have to read the entire shoebox to get just the one piece that you want. So basically there we are using enzymes that nature has evolved over the last few billion years. And there's just nothing better than that.
Yeah, tell me a bit more about the kind of the usability then of this technology and the access to it, and as a consumer.
So I think it's going to be intriguing as a consumer because, again, I think the price of storing data, all of your information is going to go down. You no longer have to be selective about which photos that you want to keep or which records you want to keep or anything. It's just any digital information that you touch, you have the option now of storing securely. The other very intriguing thing is that DNA can be stored with an air gap, meaning that it doesn't have to be connected to a network or to a power supply. So if you want, I could send all of your data back to you and you could keep it for safekeeping personally. That air gap of not having to power it, not having to have a network to it, it's very interesting to a lot of both people and government agencies that worry about having their information hacked. It's essentially one more way of keeping the information even more secure.
Some of the questions we got coming in on Slido, thanks very much for those. It's great to have them to hear what you'd like to know about this technology. Somebody's asking, Michael's asking, can you modify the data once it's saved? Was it write only?
Currently, the way that we envision using it is write only. But the interesting tie-in with the previous discussion, if CRISPR actually turns into something that has higher throughput, higher selectivity, we've dreamed of being able to rewrite long strands of DNA. It's obviously not there, but so today it's write only.
And to echo Doug, it is mostly write only, but you could rewrite it. And from the point of view of Twist, we write DNA, that's our business. We love people that want to write DNA, that want to edit stored data. So we're looking forward to the time when you're able to do that.
So this is really all kind of an archiving tool, I suppose. Julian wants to know, what are the reading and writing speeds? What reading and writing speeds we're talking about? Yeah, I'm interested in that. How long to get it on there and how long to get it back up again?
Yeah, at the average rate, if you look at the aggregate, we're doing about 100 bytes per second. And if you compare that to conventional media, it's usually tens or hundreds of megabytes per second. So the speed is low relative to conventional technology. That is something that we're working on very close, very focused to try and speed that up. And there's no technical hurdles why that can't be gigabytes per second, which is our target within the next 4 years.
What do you think, Emily?
Yeah, no, absolutely. The beauty of doing biology on silicon is that it scales really well. And so right now, the technology that we use is technology from the 1980s. So we have very big features, the wafers are very small, but if you fast forward and if we were to just use silicon technologies from 10 years ago, the features becomes much smaller. and the wafers become much bigger. And at that point, it's the same chemistry, everything is the same, but the throughput goes up massively. And so right now we're working on our next silicon chip. We used to have 1 million oligos per wafer, and the next technology we're working on has 1 trillion oligos per wafer. So we are multiplying by 1 million times the number of DNA that we make in parallel. So we are skipping the billion. Trillion is the new billion.
Who are your customers for this? Are you imagining you're going to kind of try and sell it to governments initially, or is this going to go to consumers?
Initially, we're looking for commercial consumers. So the reading and writing speeds are very commensurate with video, especially handheld video cameras. And so it's not only consumers, but it's anybody that would want to archive video. And so that'll be one of the initial boutique ways that we use it. But then I think rather than it being government, we really are trying to target consumer storage right off the bat.
Microsoft wants to kind of own this, or have you got competitors who are doing the same thing?
I suspect that we'll be first to market, and there'll be quick followers. This looks like it's going to be the technology of the future, and I think our competitors will be right on our heels.
We've had a question, what's the code? What is the code? You can see that.
Yeah, so the question is it ATGC equals 1? What we've done is we've come up with a pretty sophisticated code that uses some techniques that have been used. They're called erasure codes that are used in Azure Storage today. It's a Reed-Solomon-based algorithm that encodes redundancy in it. So it's a bit more sophisticated than using the 2 letters to map to 1 and 0. And the interesting thing about it is that, as Emily said, that there's a lot of compute that we use to actually turn the 1s and 0s into the actual DNA letters.
How robust is it? How secure is it?
It's extremely robust. One of the questions is, is there any errors in the DNA? It turns out that people don't realize that on a hard drive, there are a lot of errors on a hard drive, and the industry has evolved very powerful error correction algorithms to take care of that. And the DNA that we make today, if anything, is actually too good. The quality is too high, and you could degrade that quality a lot and still be able to get the data back. So on the DNA side, we don't have a problem of errors. It's actually the opposite. And that's an opportunity to be a bit more sloppy in making the DNA, but lowering the cost, using that to lower the cost of it.
What happens if somebody steals it?
Well, if it's in our data center, our current policy when you store something in our data center is that we replicate it, and we replicate it across a couple different data centers with policies that match the country that we're replicating it. If we're storing your data and we send it back to you and they steal it, it's gone.
So yeah, you don't have access to the data, but it does not mean that they can read it, because you can apply some similar, if not better, level of encoding, such that if someone steals your DNA sample, like if they steal your hard drive, you can encode that data so that even if they read everything, even if they read all the ACGTs without the decoding key, they still can't know what it was. But of course, you don't have the data yourself. But that's the beauty of DNA. Because you can make a lot of copies, you can have a copy at home, a copy at your bank, a copy to friends. So you can have a lot of redundancy. So overall, I think it's a lot safer than a hard drive.
I'm still curious to kind of know what the product looks like. Am I going to get a thing that sort of looks a bit like a USB key, or what's it going to look like?
The safest way to send it back to you so that it's the most stable, meaning that it doesn't accidentally get wet or get exposed to too much heat, is that we'll encapsulate it in these glass beads and send it back to you. And so it'd be a little container that would look like microscopic glass beads that we would send back. And then to read it, it needs to be put into something that is a DNA sequencer. Today we're using standard commercial sequencers produced by Illumina, so you could imagine at some point in time those sequencers would not necessarily have to be in a Microsoft data center, but they could be, at a drugstore. There are some DNA sequencers today that are about the size of a USB key. It's remarkable how small the sequencing side of DNA is happening. And so all of the reading stuff, the throughput is being pushed very dramatically, as well as the size of the sequencers, or the reading part of the DNA is being pushed by all of the biological requirements of people wanting to read their own genomes.
This technology, when we were talking on the phone, you were saying there's basically thousands of years worth of stability out of this. That basically it's not going to break, and nobody's going to be able to kind of break into it. You're going to be able to store the information almost forever, right?
Yeah, because you can go in Siberia, find a frozen mammoth in the ground, right, with fungi, with bacteria, 20,000 years old, like in the worst environment possible. And you crack the bone and you scrap the DNA, and it's there. You can read it. It's 20,000 years old. If you put your computer there, it won't last 20 days. And so that's in a bad environment. So now if you put it in a good environment where you remove moisture and you remove oxygen, it lasts forever. There are papers where they take DNA and they bake it to simulate hundreds of thousands of years of aging, and it's great. It's perfect.
Have you done experiments on this, Doug? Have you kind of tried to destroy some?
Yeah, we have, and it matches Emily's reference to that paper. Is that we've been heating it and doing lifetime experiments, and it's incredibly robustly stable. When we work out what the product specifications are, we're talking about guaranteeing the lifetime of this data storage for something that's thousands of years. Whereas today, the most that anybody will guarantee for tape is 30 years, and typically that's guard banded down to 10 years. So we're looking at improving the reliability of the way that we store information by more than 100 times.
Well, let's imagine it's in a fire and then it spends a long time at the bottom of the ocean or something like that. Is it still going to be okay?
The fire is a problem.
Okay.
So DNA, since we're made of DNA, the model of what constitutes destroying DNA, our DNA mapped to data storage, and so too hot is really going to be a big issue.
Hence the glass beads, right?
Yeah, hence the glass beads.
Yeah, and hence the redundancy. If you have your data in two different locations, there's a fire somewhere, you're fine. You have the other copy. And if you want 1,000 copies in 1,000 different locations, you can do that. So you can ensure yourself quite a bit.
How do you know it's your glass bead and you haven't got it mixed up with somebody else's?
Well, if we keep it in the data center, we're very good at that with the way that we track things. If we send you back your data and you mix up your glass beads, we can still we could recover it if you send us all back. There's ways that we encode redundant information into the strand itself that would allow us to disaggregate or remember which piece came from which files.
But the glass bead really was all about that kind of robustness that you needed for.
Yeah, the glass bead is just it's a convenient container. If you view it that way.
Are there other things that you've looked at for that?
Yeah, actually, there was a storage technique that came out of France in Bordeaux. They use things that look a little bit like brass. You have one. Brass casings from
Oh, here we go.
Oh, yeah, there. So that's a
Let me hold that still.
so that's a true product from France. It's typically filled with dry nitrogen or some other gas, and we put DNA in there. And that is also turning out. We've done accelerated lifetime testing on those, and they're extremely reliable.
How many of those have you got?
We've got about 100 of those,
Okay.
and that's a lot of data.
Would you personally, Doug from Microsoft, put all of your data onto this DNA tech now, if you could do it? Or have you already done it?
I've put a lot of my data
Yeah?
on it already. Yes, today.
I mean, the really important stuff, right? The
Yeah.
family photos.
Family photos. Today the problem is really the writing speed. And we've got the technique down for encoding, recovery, managing the errors, and absolutely, I would put my prized family photos on it.
Okay, Emily, would you trust it?
Absolutely, 100%.
Well, we're out of time. Thanks very much. Thanks very much to Doug from Microsoft and Emily Leproust from Twist Biosciences. Thank you.